E, H and K form a set of orthogonal vectors. Since K cross E equals to mu 0 omega H and K cross H equals to minus epsilon omega E. These two equations imply that H is perpendicular to both K and E, and E is perpendicular to both K and H. So E, H and K form the set of orthogonal vectors. Refractive index. The phase velocity of the electromagnetic wave in a dielectric medium is V equals to root over mu epsilon, whereas it is in free space mu 0 epsilon 0. This is represented as C. So for a non-magnetic dielectric material, if we take mu equals to mu 0 non-magnetic, that means the magnetic permeability is equal to the free space magnetic permeability, whereas the electrical permittivity is equal to K times the permittivity of free space, where K is the dielectric constant of the medium. Then V equals to 1 by root over mu 0 epsilon 0 K, and that is equals to C by root K. And as we know, the refractive index of the medium is equal to the velocity of light in free space as well as the velocity of light in that very medium. A light is an electromagnetic wave or electromagnetic radiation. Then N equals to C by V is equals to 1 is equals to root K. If this K is independent of the frequency, angular frequency omega, then it is called non-dispersive medium. The ratio mu 0 by epsilon 0 under root is called the wave impedance. This is the wave impedance for free space, and similarly the wave impedance for a particular medium is root over mu by epsilon. In case of conducting medium, the four Maxwell equations are changed. As the first equation is divergence E equals to 0, the second equation becomes divergence H equals to 0, third equation becomes curl E equals to minus mu del H del T, and fourth equation becomes curl H equals to sigma E plus epsilon del E del T. We have taken rho equals to 0. Because in case of conducting medium, we have no need to take the statical charge density. So if we take curl of this equation, then we get curl of E equals to minus sigma mu del E del T minus epsilon mu del 2E del T2. Similarly, if we take curl of this equation, then we get curl of H equals to minus sigma mu del H del T minus epsilon mu del 2H del T2. By using the vector identity, curl of A equals to divergence of a grad of divergence A minus grad square A, we can get grad square E minus sigma mu del E del T minus epsilon mu del 2E del T2 equals to 0, and also a similar equation for H. We can generalize this equation as grad square psi minus sigma mu del psi del T minus epsilon mu del 2 psi del T2 equals to 0. Now, considering the transverse field in the conducting medium, we can take the solution psi equals to psi 0 e to the power I k dot r minus omega t. Substituting this in this equation, substituting this plane wave solution in the differential equation, we get minus k square plus I sigma mu omega plus mu epsilon omega square of psi equals to 0. And since psi is arbitrary, the term in the bracket is 0, and we get k square equals to mu epsilon omega square into 1 plus I sigma by omega epsilon. And taking k समान alpha plus I beta, we get k square equals to alpha square minus beta square plus I into 2 alpha beta. And then comparing the real and imaginary parts, we get alpha square minus beta square equals to mu epsilon omega square, whereas 2 alpha beta equals to mu omega sigma. And then from these two equations, we can find alpha square plus beta square. And then we also find alpha square and beta square by adding this expression and this expression. One time adding and one time subtracting. Then we get alpha square and beta square, and also alpha and beta. So psi equals to psi 0 e to the power I alpha plus I beta n hat dot r minus I omega t. That is psi 0 e to the power minus beta n hat dot r into e to the power I alpha n hat dot r minus omega t. So this is the general equation for E and H, general solutions. That means the field amplitudes are spatially attenuated. Attenuation means it is related to some spatial damping. E to the power negative term always gives some decrease with the increase of beta. Then beta is a measurement of attenuation, and this beta is called attenuation constant, attenuation coefficient.